where we started with all this look on quadratics is where we finish as well. If you remember, we started with the T11 stuff and we were just talking about locus. And we sort of end there as well. So locus problems. Okay. Basically the idea is to get rid of the parameter, because now that we've talked about parametrics, we can look at locus in a different way. Okay? So we get rid of the P's and Q's, if you like, or whatever the parameters happen to be. You're always going to find the locus of a point. Because remember, locus is how a point moves. A point moves so that it's always 2 units away from the right, and that sort of thing. So it's always going to be a point. So I guess the first step is to find the coordinates of the point in terms of the parameters. So then we just need to find that relationship, because remember that's what locus is, the relationship between the x and the y values. So we want to get rid of the parameters, because we want to end up with an equation which is true, y equals x squared, whatever it happens to be, but no longer has any parameters in it. Now I reckon there's basically 3 types. The first type's the easiest of them all, where that once we've worked out the coordinates, already in either the x or the y value, there is no parameter. So for instance, you might do all your work, you come up with this coordinate, p plus q, negative 3. And what it's basically saying is it doesn't matter what the parameter is, it doesn't matter what p or q is, the y value is always negative 3. So therefore that's the locus. If I was to draw all these possible points, then I must end up with the line y equals negative 3. So as I say, that's probably the easiest of them all, where basically the work's been done for us. So locus is y equals negative 3. The second type is what I call ones which I think have just an obvious relationship. Usually there's only one parameter. And that's when, okay, make the parameter the subject in one, substitute it into the other, and then the parameter will disappear. So something like this. 6t, t squared plus 1 we might have ended up with. So I'll say, all right, well I know x equals 6t, so I can make t the subject. I get x over 6, sub it into the t squareds, and I've now got something which doesn't have a parameter in it. I've got y equals x squared on 36 plus 1. So that's what I call an obvious relationship. The third type is when there's not an obvious relationship, and you might need to use a third piece of information. Might be something that you've proven already in the question. And I guess the classic that we've seen already is that focal chord question that we looked at yesterday, proving that it's always on the directrix. Okay? And we use the relationship PQ equals negative 1 to prove that. So we might end up with p squared plus q squared, p plus q. And somewhere in the question we've already worked out that PQ is 3, say. So what's the relationship? Well, x is p squared plus q squared. This is where I can go back to the idea that we saw in sum and product of roots, where we said, oh, well look, p squared plus q squared I can rewrite as p plus q all squared minus 2pq. And I know that p plus q, well that's y. And pq, we worked out that that was 3, so I can sub in, and there it is, x equals y squared minus 6. So we might need to use some third piece of information that we've already worked out, or they've given us in the problem. Okay, let's have a look at some HSC ones. So 2005, they had this one. So standard sort of one, 2AP, AP squared, 2AQ, AQ squared. On our basic parabola, x squared is 4AY. They gave us the equation of the normal, so we didn't have to work it out. And then, of course, the normal at q must turn out to be x plus qy, and so on. So the first part of the question was, show that the normals intersect at our typical point of intersection. Well, I'm not going to bother doing that, because we've done that sort of question before. The second part, then, is they've told us that the equation of the chord, so again, we didn't have to work it out, they gave us the general equation, but if it passes through node A, in other words, it's a focal chord, show that PQ equals negative 1. So there's that relationship between P and Q they want us to find. Now with this one, because we've got the equation of the chord, the quickest way is to substitute in the point node A, and we get PQ equals negative 1. Okay, so let's move to the bit I'm interested in, the locus part. So now we have coordinates for R. They want us to find that locus if PQ passes through naught A. So in other words, we now know we can use the relationship PQ is -1. R, remember, was the point of intersection of the two normals. So the X value was minus APQ P plus Q. So I'm going to rearrange that. Remember, we've proven PQ is -1, so I can get rid of the PQ. And I end up with P plus Q is X on A. The Y value was A outside of P squared plus PQ plus Q squared. But, again, I can use the idea that P squared plus Q squared is P plus Q all squared. Minus 2PQ, but we've got a plus PQ in there, so it becomes minus 1 lot of PQ. Now, the PQ we know is -1. And P plus Q we just worked out was X on A. So I can sub in there and tidy that up, and we get our locus, X squared on A plus 3A, Y equals. Let's try another one. Once again, standard parabola, 2AP, AP squared, 2AQ, AQ squared. This time, they've given us the equation of the tangent, so we don't have to work that one out. So TX minus AT squared. We have to show that the tangents intersect at our standard one there. So again, I'm not going to do that now. We've done that a couple of times already, but we'd come up with A, sum of the parameters for the X value, and A times the product for the Y value. They've then given us some information. As P moves, or varies, the point Q is chosen, so the angle POQ is always a right angle, where O is the origin. So this is going to create a relationship between P and Q that I'll be able to use. So if POQ is a right angle, then I know the slope of OP times the slope of OQ would be -1. So plugging that into our slope formula, eventually we'll come up with a relationship. No, keep going. There it is. Turns out that PQ is -4. I've left off an A squared over there, haven't I? Because the A squareds do cancel. So that's not A, that's A squared. Okay, we now know that Y is APQ. So I'm not actually interested in the X value for this one, because now I've got that relationship PQ equals -4. I just look straight at the Y value. APQ. Well, I've just proven PQ is -4. So Y is -4A. Voila. So it's that sort of idea. Basically, get rid of the P's and Q's. Sometimes, and HSC questions are classics for it, you have to come up with another relationship between P and Q so that you can help you do it. Hopefully, they give us an easy one where it's obvious, and I go, oh, bang, there's the answer.